Welcome to Calculus. Today we will investigate finding derivatives of functions at any value c, focusing on the algebraic limiting process to create a derivative function using the definition. We'll take a look at three examples. The first is a linear function. The second two are both quadratic. So in previous videos, we've looked at finding the derivative of a function at a specific x value that's defined as a number. The task is different here. We want to find a derivative function, and so the definition of the derivative that we want to use is slightly different in its form. So let's give that to begin. So what we'll use as the derivative definition for this task, where I'm trying to create an actual derivative function, is this limit. So it's the limit as h approaches 0. So all of a sudden you note something different. If we compare it for just a moment with the one we've been using, the limit as x approaches c, somehow I have to account for this h. Let's just write out the original one that we've used of f of x minus f of c over x minus c. So that's the definition that we had used to calculate a derivative at a specific x value. So somehow we need to figure out, why am I using h below? So before we fill in that whole limit expression, let's say where that is coming from. So if I have a plane here with a given kind of arbitrary green function, recall the way that we had defined the derivative was by letting a secant line pass through the function, and then we had defined these 2 points where that secant crosses through our function as c and x, but we're doing so differently now. This left point I want to call x, and the right hand x value I don't want to label directly, but I just want to note that it is a distance of h away from x. So we kind of see that h appear in our limit. We're saying we're going to limit that down to a distance of 0. So it's the same idea. We're going to let this right-hand point limit over towards the left one. We need to decide how to label that right-hand point. Well, if it's h to the right of the x value, we could label it as x plus h. We also need to figure out what would our y values be labeled as. So if I trace over to y-axis and use the idea of that being the point x plus h in terms of its domain value, its range would have the value of f at x plus h. We can also label the range value that's generated from the domain value of x by calling it f at x. So it's the same idea as our first definition, but it's defined in terms of distance instead of 2 distinct x values. So we know what h is now. H is the distance between those 2 x values. So our limit expression here is going to be f at x plus h, that's the upper y value, minus f of x over x plus h minus x. So one thing we do need to notice is that in our denominator, there's a cancellation there. X minus x is going to cancel. And that gives us this derivative definition that we're going to use for these 3 examples. The limit as h approaches 0 of f at x plus h minus f of x, all divided by simply h. So simpler denominator for sure. And again, I just want to label this as the difference quotient. That is the name of that form of the definition of the derivative. Well, let's apply it to our question here. So we want to define how these things are going to fit inside that limit. So I've got my f of x here. That's 4x minus 4. And I can define f at x plus h according to that same rule, but instead of x, I'm going to compose in that new domain value of x plus h. So this is 4 times parentheses x plus h, that's where x was, close parentheses minus 4. So it's a little simpler also in terms of setup. At this point, I just need to plug in those two substitutions. So we want to calculate the limit as h approaches 0, so as the distance between the two x values decreases to nothing, of f of x plus h is 4 times x plus h minus 4, and I put that in brackets, minus f of x itself is simply 4x minus 4. And that is all over simply h. So clearly the numerator has the vast majority of the simplifying there. So we'll start with the distribution of that 4 through the x plus h. So the next step would give us the limit as h approaches 0. In my numerator now I've got 4x for the first distribution plus 4h minus 4. And then I've also got to distribute this negative. I can think of it as a -1, distributing it through that binomial. So that's minus 4x plus 4 all over h. So as we look here in my numerator, we got several cancellations. 4x minus 4x will cancel. Minus 4 plus 4 cancels. And so this really reduces down to simply the limit as h approaches 0 of 4h over h. And then again, I see an additional cancellation of the h's by division. And this is simply the limit as h approaches 0 of 4. And recall, when you don't have a variable there in your limit function, you just simply write 4. So what we see is that when we take the derivative of a linear function, what we're left with is simply a constant number. So I could write this as f prime of x, remember that's our notation for a derivative, equals 4. And again, I do want to emphasize that what we're writing here is not a specific slope at a specific point on the function. It is a function that tells me the derivative of the original function at any point x. Turns out that the slope of any point on a line is 4. Let's see how that works for a quadratic function. So here I've got the function 5x squared plus 5. So again, we'll bring our definition that we're using of the derivative, which again, it's this difference quotient, the limit as h approaches 0 of f at x plus h minus f of x all over h. Again, we just want to define those two numerator values first. So what's f at x? F at x is 5x squared plus 5. It's the original. And then the second one, really the one that comes first there, f at x plus h. Again, it's a composition. I'm taking x plus h and I'm composing it into the function anytime I see x. So that's 5 parentheses x plus h squared plus 5. before I plug that into the green derivative definition there, I do want to expand and simplify this f of x plus h statement. So that's a double distribution of FOIL. I'll expand it there so we can see it. So I'm going to distribute x to both x and h. So that becomes 5 times x is x squared plus hx, and then the inner term is the same, plus hx. So I see those will combine. And then the last term's plus h times h, or h squared. And then we can simplify this down a little bit. It's 5 times x squared plus, there's 2 of those hx's, so I'm going to call it 2hx plus h squared plus 5. And at that point, I could distribute this first 5 through that trinomial. So that's 5x squared plus 10x, or hx, plus 5h squared plus 5. So that's what we'll use when we substitute in f of x plus h. We've made it into a polynomial. So let's take these two expressions, plug them into our green derivative definition. This is the limit as h approaches 0 of f of x plus h. So that is that expression we just expanded. So in parentheses, 5x squared plus 10hx plus 5h squared plus 5. And then I'm going to subtract from that the original, f of x squared plus 5. 5x squared plus 5. And I'll put in the denominator just h. Our next simplification will be combining like terms in the numerator, seeing if we can cancel anything. So just taking a look there, I've got 5x squared minus 5x squared. In fact, what I'll do, I'm going to let the parentheses on the first one go and then distribute this minus sign so that both of these terms become minus. So we can see the cancellations more easily. 5x squared minus 5x squared cancels. 5 minus 5 cancels. And so what we're left with in our numerator is 10hx plus 5h squared over h. Almost ready for direct substitution. What I need to cancel is the h now. So I see a factor of h in each term in the numerator. So I'm going to cancel one of each with the denominator h. And what we get as a final limit expression before we perform the direct substitution is the limit as h approaches 0 of 10x plus 5h. And at that point, we are ready to perform direct substitution. So now what we've got is 10x. So notice I don't substitute anything for x because x has nothing to do with the limit. But where I do substitute zeros for h, so it's 5 times 0, that term will cancel, and the limit here is 10x. And again, our interpretation is that's a function. The derivative function for f of x, or f prime of x, equals 10x. So we've taken a look at one linear function, found its derivative. It was a constant. We've taken the derivative of a quadratic function, and we can see that its derivative is linear. So let's see if that's always the case with quadratic functions. And let's work on a more complicated quadratic that has all three terms. It's a trinomial. So here is our third example. It's y equals 3x squared plus x plus 4. Like we've been doing, we want to use our definition of the derivative that involves that distance h. So the limit as h approaches 0 of f at x plus h, that's that upper y value, minus the lower y value f at x, all over simply h. So we know at this point that f of x is my original function, 3x squared plus x plus 4. My f at x plus h, again, I need to compose x plus h, in this case, in two spots, wherever I see x in the original. So this is 3 times x plus h squared plus x plus h plus 4. So I think that this is a good moment to simplify that, save some work later in the fraction. So I'm going to expand this. This is 3. And again, this is the same x plus h squared. So before we found that was x squared plus 2hx plus h squared, if I FOIL that out. And then I can let these parentheses go, x plus h plus 4. Now I want to distribute that 3 through the trinomial. So this will be 3x squared plus 6hx plus 3h squared. And then again plus x plus h plus 4. And it turns out that there's no like terms there. So I got to put that 6-term polynomial in for f at x plus h. Let's do so. The limit as h approaches 0 of this blue polynomial, 3x squared plus 6hx plus 3h squared plus x plus h plus 4 minus my original function in the red, so that's 3x squared plus x plus 4. And then what I want to place that over is, again, simply h. So for my next limit expression, it's limit as h approaches 0. Again, I'm looking for cancellations. So the first group is distributed through, so we're good. Second group, I need to distribute this negative, which is going to make all the signs negative. That's an x. So let's see if we've got any cancellations in our numerator. So 3x squared minus 3x squared definitely will cancel. Plus x minus x and 4 minus 4. So that, again, what we're left with in our numerator is a much simplified version here of the original numerator. It's 6hx plus 3h squared plus h all over h. Still, we've got some cancellations we can observe. So I see that I've got h again in the denominator, and I have in each of the terms in the numerator an h, so one of those will cancel out of each term along with the denominator. So that now we simply have the limit as h approaches 0 of 6x plus 3h plus 1. Now I'm ready to use the direct substitution to evaluate that. So again, there's nothing about x in the limit. It's as h approaches 0. So this is 6x plus 3 times, instead of h, I'll place 0 plus 1. And our derivative function for this quadratic is 6x plus 1. We'll call that f prime of x, the derivative of f of x. And to follow up with an answer to our question from example 2, it seems that at this point, anytime that I take the derivative of a quadratic, it is a linear function, because that new derivative there that we just calculated, 6x plus 1, is also linear. Thank you for joining for these 3 examples of finding derivatives for functions using the definition to generate derivative functions. I'll let you go work on your problems. Thank you for joining. See you soon.